June 2026. Two starships floating 300 miles above Earth. One is nearly empty, the other packed with 200 tons of frozen fuel colder than -200 degrees Fahrenheit. SpaceX is about to attempt something no one has ever done at this scale, pumping cryogenic propellant between two separate spacecraft in orbit. But here's what makes this absolutely insane. One wrong move, one leak, one failed seal, and both ships could be lost. So why is Elon Musk betting everything on this? Here's what most people don't understand about this mission. It's not just a test. It's the linchpin holding together humanity's return to the moon and eventually Mars. NASA's Artemis 3 mission, scheduled for September 2028, can't happen without it. The astronauts can't land on the lunar surface without a fully fueled Starship waiting for them in orbit. And to get that Starship fueled, SpaceX needs to perfect this transfer technique first. Right now, between January and March 2026, SpaceX is racing to prove version 3 Starship works. This isn't the same ship that's been flying test missions. V3 is stretched longer, carries bigger propellant tanks, and features a completely redesigned heat shield. The thruster system has been rebuilt from scratch. Every single one of these upgrades exists to solve one brutal problem: surviving re-entry while carrying enough fuel to actually do something useful in space. But here's where it gets really interesting. Unlike the earlier versions that just touched the edge of space and came back down, version 3 must achieve true orbit and stay there. The engines need to restart in the vacuum of space, something that sounds simple until you realize there's no air pressure to help ignite the fuel. One failed restart and the ship becomes a 100-ton piece of orbital debris. How many test flights will it take to get this right? SpaceX isn't saying, but flights 12 through 15 are all V3 tests. Then comes April and May, and this is where things get wild. SpaceX wants to catch a returning Starship with Mechazilla's giant chopstick arms. Not the booster, they've already done that. They want to catch the actual ship, all 165 feet of it, as it descends back to the launch tower at hundreds of miles per hour. Think about the precision required. The ship is coming in hot. The arms have maybe a 2-foot margin for error, and one miscalculation sends 200 tons of stainless steel crashing into the most expensive piece of ground infrastructure SpaceX owns. Why rush to perfect this before June? Because catching both stages means SpaceX can relaunch them within hours, not weeks. And for the refueling demo, they'll need multiple launches happening in rapid succession. The math is unforgiving. Each tanker Starship can only fill about 15% of the receiver ship's tanks. That means somewhere between 10 and 20 separate flights just to fuel one mission ship. Without rapid reusability, the whole concept collapses under its own weight. Now let's talk about what's actually happening in June 2026. Two Starships launch within weeks of each other. The first one, the tanker, reaches orbit and waits. The second one, the receiver, launches and begins the delicate dance of orbital rendezvous. As SpaceX's Dan Hewitt revealed during the Flight 11 webcast, both ships now carry specialized docking adapters on their noses. These aren't like the simple hatches on the ISS. They're engineered to handle connections under extreme thermal stress, while transferring propellants that would freeze your hand solid in seconds. The docking itself is only the beginning. Once connected, SpaceX faces a problem that stumped engineers for 60 years. How do you pump liquid fuel when there's no up or down? In microgravity, physics works against you. The liquid methane and oxygen don't sit at the bottom of the tank like water in a bucket. Instead, they coat the tank walls in a thin layer while gas bubbles float randomly through the middle. Try to pump that, and you'll just suck gas instead of fuel. Your pumps cavitate, your engines can't ignite, and your mission is over. SpaceX's solution is brilliantly simple, yet incredibly difficult to execute. They fire small ullage thrusters on the side of the ship, creating just enough acceleration to push the propellant to one end of the tank. It's not much, maybe 1/10 of Earth's gravity, but it's enough. The liquid settles, and then SpaceX uses the pressure inside the tank itself to squeeze the fuel through the transfer lines. No pumps, no moving parts, just pure pressure differential, pushing 200 tons of cryogenic propellant from one ship to another. But even if the transfer works perfectly, there's still the boil-off problem. These fuels are stored at minus 297 degrees Fahrenheit for methane and minus 298 degrees for liquid oxygen. Any heat source, sunlight, electronic components, even the friction of fuel moving through pipes, causes evaporation. SpaceX estimates they lose about 2 to 5% of their propellant per day just sitting in orbit. That's why the depot ship becomes critical. This is where SpaceX's three-part architecture reveals its genius. First, there's the depot, a specialized starship that never comes home. It has no heat shield, no flaps, no re-entry hardware. It's just a massive 1,200-ton orbital gas station designed to minimize boil-off and store propellant for months. Second, the tanker fleet. Reusable starships that ferry 100 to 150 tons of fuel per flight from Earth to the depot. And third, the mission ship, the starship that actually goes somewhere after being fueled up. Here's what makes this revolutionary. A single starship holds roughly 200,000 gallons of propellant. That's more than twice the entire mass of the International Space Station. The ISS took 30 missions and over a decade to build. SpaceX wants to fill an equivalent mass in fuel with 10 to 20 flights over a few weeks. The scale is almost incomprehensible, but it's the only way to make deep space missions economically viable. And this brings us to something fascinating about history repeating itself. Back in 1960, NASA engineers proposed almost exactly this same architecture. They called it Earth Orbit Rendezvous. The idea was to launch 10 to 20 smaller rockets, dock them together in orbit, and assemble a spacecraft larger than the Saturn V. They'd refuel it in orbit, maybe even leave a fuel depot on the moon for future missions. But 1960s technology couldn't handle it. Docking was primitive and dangerous. Pumping cryogenic fuel in zero gravity was unreliable, and the cost of launching hundreds of rockets with expendable hardware would have bankrupted the program before it even started. So NASA chose Lunar Orbit Rendezvous instead. One big Saturn V, one small lunar module. Get in and get out fast. It worked, but it was a dead end. Apollo 17 landed in 1972, and we haven't been back since. The trade-off was enormous. All 6 Apollo missions combined brought back just 842 pounds of lunar samples. No permanent base, no infrastructure, no foundation for future exploration. Just footprints and flags. Why? Because without refueling, every gram of fuel had to be launched from Earth in one shot. The rocket equation is merciless. To add 1 pound of payload, you need exponentially more fuel, which requires a bigger rocket, which needs even more fuel. The whole thing spirals out of control. SpaceX is breaking that equation. With reusability and orbital refueling, the economics finally work. A Starship launch costs roughly $50 to $100 million in marginal costs. If they need 15 tanker flights to fuel one Mars mission, that's $750 million to $1.5 billion in fuel delivery. Expensive, yes. But compare that to building a rocket big enough to do it in one launch. That rocket would be physically impossible to build with current materials science. So why do all this refueling in low Earth orbit specifically? 3 reasons, and they're all critical. First, energy efficiency. Reaching LEO requires about 9.4 kilometers per second of delta V. Getting to Mars from LEO takes another 3.6 kilometers per second. But launching directly to a Mars trajectory from Earth's surface would require combining both, and the rocket equation makes that prohibitively expensive. By refueling in LEO, SpaceX can treat it like a two-stage journey where they only pay the LEO cost multiple times with smaller, reusable vehicles. Second, safety and debris mitigation. If something goes catastrophically wrong during refueling, a ship explodes, propellant leaks, systems fail, the debris won't stay in orbit forever. At LEO altitudes of 200 to 300 miles, atmospheric drag still exists. Any debris will naturally decay and burn up within months or years, rather than becoming permanent space junk that threatens other missions for decades. Third, and perhaps most important, LEO is where every deep space mission has to pass through anyway. Whether you're going to the Moon, Mars, or the asteroid belt, you first have to reach orbital velocity around Earth. That makes LEO the perfect staging point, a cosmic truck stop where ships can top off their tanks before burning for distant worlds. But here's the question nobody's asking. What happens if this June 2026 test fails? If the June test fails, SpaceX simply tries again. That's the entire point of rapid reusability. Failure isn't catastrophic, it's data. But here's what makes this timeline so tight. NASA's watching every single test. Artemis 3 astronauts are training right now for a mission that depends entirely on SpaceX, proving this works. The pressure is immense, but the opportunity is even bigger. Because if SpaceX succeeds, June 2027 brings the next milestone, an uncrewed Starship landing on the Moon. Not just orbiting, actually touching down on the lunar surface, fully fueled through orbital refueling. That's the full dress rehearsal for Artemis 3 in September 2028, when NASA astronauts will finally return to the Moon after 56 years. And it all hinges on those two Starships docking in orbit 18 months from now, transferring 200 tons of frozen fuel while traveling at 17,500 miles per hour. This isn't just about the Moon. Once SpaceX proves orbital refueling works, the entire solar system opens up. Mars missions become possible. Asteroid mining shifts from science fiction to engineering problem. Deep space telescopes can be serviced and refueled instead of abandoned. We're watching the moment that spaceflight stops being about flags and footprints and becomes about infrastructure and permanence. The 1960s engineers dreamed of this. Elon Musk is about to make it real. What do you think? Will SpaceX pull off the June 2026 refueling demo on schedule, or will we see delays? Drop your predictions in the comments. If you want to stay ahead of every development in this story, hit that subscribe button for new space review and turn on notifications. Like this video if you're as excited as I am about what's coming, and share it with anyone who still thinks we're not living in the golden age of spaceflight. We're just getting started.